Welcome to Chapter 9 from my second year module Mathematical Analysis, and this is a chapter about sequences of functions, and especially about uniform convergence and pointwise convergence. There are 3 sessions in this chapter. The first session lasts about 11 minutes, the second one lasts about 46 minutes, and the last one lasts about 22 minutes. The first session, the original sound recording failed, and so I have to add annotation afterwards. The second session was affected by a couple of typos at the very end, and I'll remind you about that before the second session starts. I've combined all 3 sessions into one 1 hour 20-minute video. So this is Chapter 9 on sequences of functions, and this is a narration after the event as the audio recordings failed on the 24th of November. Anyway, the point of this chapter is to tell you about what happens if you've got sequences of functions defined on a domain, and in this case taking real values, though you could be taking values in some other r to the d. So you've got a sequence of functions, f1, f2 and f3, and you want to find out whether they can have some sort of a limit or not. Now, it's not the same as a sequence of numbers, but it's still interesting to know whether or not a given sequence of functions can approximate some other function or not. This can be important when you're trying to solve some differential equation and you want to look at approximate solutions, and you want to know how close your approximate solution is to the limit function, and a lot of other settings. And it's very important later on in more advanced analysis as well. There are quite a lot of different notions of convergence, but we're going to focus on 2 of them, called uniform convergence and pointwise convergence for sequences of functions. And to help us, we'll just have a look at reminding ourselves about my notion of absorption that we looked at earlier in the module. You may remember that we had the notion of a set absorbing a sequence in r to the d if from some term onwards all terms in the sequence, all elements of the sequence were in that set. So the sequence eventually gets stuck inside the set. Now, we had an exercise on a question sheet, and this is a slight variant on it, and it's not very hard. If you want to check whether a sequence of real numbers converges to an element of the real numbers, well, usually you would use open intervals, but if you use closed intervals instead, then you get an equivalent definition. This is even though the fact that a particular closed interval absorbs the sequence doesn't force the sequence to be stuck inside the corresponding open interval. Nevertheless, if you know it works for all of the closed intervals centered on A, then it does show that it works for all open intervals centered on A as well. We proved this, in fact, in generality using closed balls and open balls in r to the d. So this is, in fact, a special case of a result we did in an earlier examples class. So that brings us on to the notion of pointwise convergence, and this is, of the 2 notions of convergence for sequences of functions, this is slightly easier than the other one, than uniform convergence. This one is you just look separately at each point x in the domain, and remember that fn is a sequence of functions defined on D, taking values in R. So then for each x in the domain, you get a sequence corresponding to x of real numbers because they're taking values in R. So if you like, n can vary, x can vary. If you fix a particular x and let n vary, you get a sequence, fn of x as n goes from 1 up to infinity. And now you can ask then, does this approach the right limiting value, f of x? Does fn of x tend to f of x as n tends to infinity? So you look at x in D, you take a particular x in D, you look at this sequence, f1 of x, f2 of x, f3 of x, that's a sequence of real numbers. And you ask, does it converge to f of x? Now you might get different answers at different points x. So it might be that at some values of x, this sequence does give you a sequence converting to f of x, and at other values of x, it doesn't. To say that the sequence converges pointwise to f, the sequence of functions converges pointwise to f, if you actually get that this limit is correct at every point of x. So you have to look for all x in D, look at the sequence, does it converge to f of x? If that works for every x in D, then you say you've got pointwise convergence of the sequence fn to f. It's not a very strong notion of convergence, in fact, and it doesn't have very good properties. But it is a useful starting point when you want to understand some of the other notions of convergence. Now, uniform convergence is a bit trickier. But before we move on to uniform convergence, and before we look at closed ball and sets involving sequences of functions, let's have a look at a particular example illustrating pointwise convergence of a sequence of functions. So let's consider the following functions defined on the real line. So fn will go from R to R, and which functions are they? Well, we'll just define fn of x to be x divided by n. So again, remember, n can vary and x can vary. It's almost a function of two variables, but we think of it as a sequence of functions of x, and we'll be fixing x and letting n vary. So fn of x is going to be x over n. And we're going to have a look and see what these functions look like and what they do. So I'll leave it to you to check some of the details of this in full. But let's at least have a sketch and see what these functions are doing. So here we are, let's have some axes. And f1 of x is just x, so our first function is just x, the second function is x over 2. And so you can see what these functions are. Fn of x is x over n. So you can see we've got a very clear formula for what each of these functions are, and we can sketch them, and you can see we get a sequence of graphs. So here's the first function. That's y equals f1 of x equals x, which we sketched in blue. And now in red, we'll do y equals f2 of x, which is x over 2. And we'll do x over 3, which is f3 of x. Now each of these is, of course, a straight line with a positive gradient. So the gradient get rather small when n is big, but if you look at any one of these, it's a straight line with some fixed positive gradient, and it heads off to minus infinity when you go left, it heads off to plus infinity when you go right. So each of these functions is unbounded. But now if you fix a particular point x and look at the values taken by these functions, here let me show them on the y-axis, then of course the first value, and it looks like I'm not completely to scale here, but that can happen. So f1 of x is x, f2 of x is x over 2, f3 of x is x over 3, and as you can see, fn of x is tending down to 0 as n tends to infinity. Well, tending to 0 as n tends to infinity. So the functions fn are converging to the function f pointwise where f is a constant function 0. That's f of x is 0 for all x. Which shows you that a sequence of unbounded functions can converge pointwise to a bounded function. And that'll do for today. Okay, that brings us on to the second of the 3 sessions. And this time the sound recording was fine, but I made a couple of typos at the very end. In the penultimate sentence, about 45 minutes into this second session, where I wrote 2 to the n, where I should have written 2 to the minus n. Well, 2 to the little n, where I should have written 2 to the minus little n, and then 2 to the big N, where I should have written 2 to the minus big N. In other words, I missed out a couple of minus signs. So I hope you watch out for those. So we were talking about sequences of functions, and we're looking at pointwise convergence and uniform convergence. Last time we looked at pointwise convergence. So you had this sequence of functions all defined on the same domain D. So you've got functions f1, f2 and f3 all defined on D, and you want to know what's the behaviour as n gets large. Do these functions approach some other function in the limit? So I reminded you about a couple of things to do with convergence and absorption. And then we'd looked at the definition of pointwise convergence, which was simply that if you look at each point one at a time, take any particular point in D, and you look at what happens as n gets large, so you fix x and let n vary, then you get a sequence fn of x varying as n tends to infinity. Does it tend to something? If it does, then that's your limit function defined at that point. For it to converge pointwise, it has to work separately at each point. You get a different sequence probably at each point, and you try and see whether it's got a limit at every point. If so, you've got pointwise convergence, converging pointwise to some limit. It's not a very good notion of convergence, but it is one that's normally fairly easy to establish if it's true. So we looked at a particular example here of some functions fn of x equals x over n. And now each of these is a function, it's a straight line function with some positive gradient, though the gradient might be small. So as x tends to plus infinity, for any particular one of these functions you pick, say you pick the function f2, then we know that x over 2 goes off to plus infinity as you head to infinity to the right. And as x tends to minus infinity, it tends to minus infinity. And the same is true for each of these other functions in the sequence, even though the gradients are quite small when n is large. However, if you fix a point x and let n vary, then you get a sequence of points coming down towards the axis, and you get a limit function, fn of x, f of x is equal to 0 constantly. So in fact, you could draw the limit function along the axis if you wanted. Actually, let me choose a different colour. So this is y equals f of x equals 0. And that's the limit function in this case. It's a pointwise limit. And as we'll see in a bit, it's not a uniform limit.
So our next task then is to investigate what does uniform convergence mean. What does this stronger notion of convergence mean? If you want a better notion of approximation, because you can see that although these functions are converging pointwise to 0, they're not very good approximations to 0, because if you go a long way out to the right, your functions are still going to be very, very high up. It's still a long way away from 0 if you go a long way out. For example, notice that f1 of 1 is 1, f2 of 2 is equal to, well, the second function is x over 2, so that's 2 over 2 equals 1. And more generally, well, okay, f 1,000, the 1,000th function is x over 1,000. Which looks a bit like 0, but of course, if you figure out what it does to the point 1,000, it's 1. And if you go even further out, if you apply it to 1,000,000, you get 1,000. And so on. So, although they get shallower and shallower, and they're converging pointwise to 0, they're not very good approximations to 0, any particular one of them, because the value is very different from 0 if you take a big value of x. Uniform convergence says that that's not going to happen. For uniform convergence, you're going to be close for all values of x simultaneously. None of these functions achieve that. Uniform convergence is a stronger kind of convergence. So let's have a look at what we have to do. First of all, we're going to define closed function balls. This is very like the notion of closed ball in Euclidean space, but it's going to be a set of functions instead. And the nice thing is that we will be able to sketch it. So what is a closed ball centered on F with radius epsilon? And I'm using a bold B just to show you that this is something special. This is now a ball of functions. This is a set of functions. It's those functions, real valued functions defined on D, which are close to F everywhere. So what's going on? Well, the epsilon tells you how close it's got to be. F tells you which function you're trying to approximate. And to say that G is close to F everywhere just says that mod G of x minus f of x has to be less than or equal to epsilon for all x in D. Which is another way of saying that is that G of x should be in the closed interval f of x minus epsilon, f of x plus epsilon. It's got to be between f of x minus epsilon and f of x plus epsilon. But that has to be valid for all x in the domain. So it's a set of functions. And now let me sketch for you what sort of functions you're dealing with there. Let's assume that we're dealing with a function from R to R. So suppose D equals R for this diagram. Then you might get a picture something like this. So let me draw a possible function y equals f of x. Then let me draw you y equals f of x plus epsilon and y equals f of x minus epsilon. So I have to go up and down epsilon. Let's have a completely different colour. So I'm attempting to go parallel. So this is y equals f of x minus epsilon. And this is y equals f of x plus epsilon. And now, what sort of functions g am I going to allow in your function ball? The function ball are those things that stay between f of x minus epsilon, f of x plus epsilon inclusive. So it's got to stay between those two green lines. So a typical function g, it's allowed to go anywhere between these two lines. It has to be a function, of course. So this is y equals g of x in red. So for g to be in the function ball, centered on the function f, remember that's a set of functions. Which functions g are allowed? It's those functions that stay between those two green lines. So I guess I could sketch that to show you where this is sort of a sketch of your function ball, except what you're allowed in there is any function that stays stays in that band. Okay. So for g to be in the function ball, the graph of g must stay inside this curvy, this what I'll call the curvy strip. And so you can think of that curvy strip as a sort of sketch of what the function ball looks like, though actually what it's really a sketch of is where the graphs of the functions are allowed to be. Now that's a special setting of functions from R to R, but it's a good way to think about what's going on. And you should also think that that epsilon could be very, very small. For example, it could be 10 to the minus 100. I think 10 to the minus 100 is very small. Imagine that epsilon was really 10 to the minus 100. Well, you couldn't possibly see the difference between the green functions and the blue functions. And any function that stayed within 10 to the minus 100 of f, you're not going to be able to see any difference if you try and draw it. So, unless you're working on a very strange scale. So this is why this is a very good, very strong notion of approximation. Staying within epsilon everywhere, so staying within 10 to the minus 100 everywhere, means that you've really approximated the function very well everywhere at the same time. The sequence of functions we looked at before didn't do anything like that because, as we saw, there were lots of places where they were miles away still. Even though, point by point, they did eventually approach zero, nevertheless, each individual function was pretty badly behaved if you went away far enough from the origin. Now, I haven't told you what uniform convergence means formally yet. You're going to get that in a second. But I hope I've illustrated to you that there is some sort of a difference between approaching just separately point by point and getting very close everywhere at the same time. Now, if you really get to grips with that, then you're getting to understand the quantifiers, what depends on what. Because, you know, does epsilon depend on x? Does x depend on epsilon? Things like that. Which way around the quantifiers go, hidden underneath this is some quite subtle stuff involving how do you order your quantifiers. If you can really get to grips with the difference between pointwise convergence and uniform convergence, that's one of the hardest, one of the subtlest distinctions and one of the hardest concepts in this module, I would say. So if you can really understand this, I think you're doing really well. Okay, so now you've figured out what this function ball is, then just as before with ordinary sequences, you've got a notion of absorption. What does it mean to say that a function ball absorbs a sequence of functions? It means that from some term onwards, all of the functions are stuck inside that function ball. So there has to be some capital N, that beyond that, all the functions are stuck inside the function ball. On question sheet 5, by the way, which is available at the front, there is an alternative approach that we won't do in lectures using something called the uniform norm. The uniform norm is, for functions, is a bit like the Euclidean norm is for vectors. It gives you a notion of distance between functions. And once you've got a notion of distance, you can define open balls, closed balls again, and you get to the same sort of thing. So this closed function ball is very closely associated with something called the uniform norm, which gives you a notion of a distance between two functions, or the distance through a function to the origin. And you can find that in question sheet 5 as an alternative approach. Don't forget to bring question sheet 5 to the problem class, the examples class tomorrow. Okay, so here we have double star. What does it mean for the function ball to absorb the sequence? It means that from some term onwards, all of the functions are stuck inside that ball. So you should imagine, from some term onwards, all of your functions have graphs stuck inside that curvy strip. And if that curvy strip has with 10 to the minus 100, that means all of the later functions are stuck within 10 to the minus 100 of your function. But in fact, it has to, you want to get uniform convergence, not just 10 to the minus 100 must do, but every positive number epsilon, no matter how small. So you converge uniformly on D means that every closed function ball, no matter how small the radius, every closed function ball centered on that function must absorb the sequence of functions. So, yes, from some term onwards, you're within 10 to the minus 100, but that wouldn't be enough because you need to know that a bit later on in the sequence, you're going to be within 10 to the minus 1,000, and so on. Whatever small positive number epsilon you choose, from some term onwards, the functions must be close to the limit function at all points simultaneously, which is what that curvy strip is showing you. It's no good being close at one point and then going further to get close to another point. That's not good enough. Here's the full definition of uniform convergence without using my notion of absorption. Because absorption, remember, is a non-standard term. So if you look in the books, you'll find something like this. For all epsilon greater than 0, there's some big positive natural number n, so that from that term onwards, all the functions are close to the function f. But notice, there's this for all x in D. And here, the distinction here, if you want to distinguish this from pointwise convergence, in pointwise convergence, capital N is allowed to depend on x. In uniform convergence, capital N is not allowed to depend on x. So this is the big difference. So uniform convergence N depends on epsilon, but not on x. Because of this notion of all x simultaneously. For pointwise convergence, N is allowed to depend on epsilon and x. epsilon and x. So again, the fact that something is happening at all x simultaneously gives you roughly, this is only rough, that the sequences of numbers are converging to the limit at about the same rate everywhere. Well, that's not a very accurate description, but it's one way to think about it. For pointwise convergence, you may well have to go much further along the sequence at some points than you have to go along the sequence at others. But for uniform convergence, that doesn't happen. We're going to look at a lot of examples now to distinguish these. Any questions before we start looking at the examples? You may well have some questions afterwards. Okay, let's look at the examples. That should help. There is a theory that one should always look at the examples first before you look at the definitions. So what you may want to do is go back and look at the definition again after you see the examples. Oh, I said uniform convergence is better than pointwise convergence. You can establish that for yourself rather easily from what I've pointed out above. If you write both definitions out in full, you get to exactly what I said, that in uniform convergence, the same n works for all x at the same time. Pointwise convergence, n is even allowed to depend on x. So uniform convergence is the better one. But pointwise convergence doesn't imply uniform convergence. And one of the examples we've already seen is the functions x over n we looked at before. So here's an exercise for you. Look at the functions fn of x, fn from r to r, where fn of x was equal to x over n. And you should be able to convince yourself, especially after we've done a few more examples, that fn converges to 0 pointwise, which I've already pointed out, but not uniformly. I'll just say aloud one way to see that, which is going to be similar to the examples we're looking at in a moment. If you look back at the sketches of those functions and then think, what would the function ball centered on the 0 function be? That's the 0 function there. So that's a function that's constantly 0. What I called a curvy strip isn't very curvy when you're looking at with centered on the 0 function, because you're just going between minus epsilon and plus epsilon. So that gives you a horizontal strip going between y equals minus epsilon and y equals plus epsilon. And that's the function ball that you're trying to get into. But it doesn't matter which value of n you look at, the function x over n is not stuck in there. The function x over n heads off to plus infinity as x gets big. So there's no way of getting inside one of these thin, indeed, you can't get inside any horizontal rectangular strip of height. So not only, you only need one bad epsilon. In the case of the function we were looking at before, all of the epsilons are bad. So it's much worse. You only need one bad epsilon to fail uniform convergence. Okay, let's have some more functions. This time, instead of the whole real line, we'll start with the closed interval 0, 1. And the functions are fn of x equals x to the n. Then I claim that this is a pointwise limit for this sequence. We're going to have to do case-by-case analysis to prove this, though I'll do the sketch first to show you what's going on. But the idea is that, well, fn of x is x to the n, so if you fix a particular x, you have to look at the sequence fn of x, fix x and let n vary and see what happens in the limit. Well, we'll do case-by-case analysis on it, but I'm going to first of all sketch sketch the sequence of functions and show you what they do. So remember, of course, we've now got a sequence of functions. f1 of x equals x, f2 of x equals x squared, f3 of x equals x cubed, and so on, and we can sketch all of those, and we can then get some idea of what's going on. And we're only working on the closed interval 0, 1. So we can ignore everything outside, and we're just going between 0 and 1. And notice the function values are also stuck between 0 and 1. And they all start at 0 and end up at 1. So notice that fn of 0 equals fn of 1 equals... fn of 0 equals 0 and fn of 1 equals 1 is what I should be saying. 0 to the n is still 0, and fn of 1 is 1 to the n, which is still 1. So they all go between these. So here's the first one, y equals f1 of x equals x. Then I can do x squared. And now actually they're going down, because between 0 and 1, the bigger the power you take, the smaller the number gets. So x squared looks a bit like this. Here's x cubed. And so on. So I've done x to the 1, x to the 2, x to the 3, x to the 4. So let's get this right. That's in blue. f1 of x is in black. f3 of x I did in red. Bit hard to label them all. I could stick arrows in if I wanted here. Okay, so what's going on? Well, they all take the value 0 at 0 and 1 at 1, but as you can see, they're getting rather shallow towards the left and getting rather steep towards the right. My purported limit function goes along the x-axis for a while, but it doesn't go for the origin, it jumps up at the end. So here's the limit function. So this is y equals f of x. And note that f of 1 equals e to 1. So I claim that's your limit function. It goes along the x-axis and then suddenly jumps up at 1. Now there's something a bit odd about this, because these functions that are the functions we're looking at are polynomials. You can't get much nicer than polynomials. X to the n, continuous, differentiable. You can't get much nicer than that. They're converging supposedly pointwise to this limit function. This limit function isn't even continuous. It's got a jump at one point. So where does it break? Well, it doesn't break at any of the finite stages, but it's one of these funny things that can happen in the limit. A pointwise limit of continuous functions can be discontinuous. We haven't proved much yet, but this is a warning. A pointwise limit of continuous functions can be discontinuous. Sometimes. Well, turns out that doesn't happen for uniform convergence. A uniform limit of continuous functions has to be continuous. So uniform convergence is better. Though we won't prove it, you are allowed to use that standard fact, and it's stated a bit later in this chapter. So this does not happen for uniform convergence. Okay, now let me prove to you that the pointwise limit is 0. And we'll do a case-by-case analysis, treating 1 as a special case. Unsurprisingly, there is something special about the point 1 here, which is where it jumps up. So we'll check the pointwise limit using case-by-case analysis. Case 1 then, suppose x equals 1, or let x equals 1, then f1 of x equals f2 of x equals, and so on, equals fn of x, they're all equal to 1. Because 1 to the n is 1. So fn of x equals 1, tends to 1, and then tends to infinity, which is what we wanted. And note, f of x is equal to 1 above, f of 1 is equal to 1, so we're good. Okay, now we look at case 2. We're working in our domain. Otherwise, consider x in closing interval 0, 1 in our domain, but not equal to 1. Then mod x is less than 1, because x is not 1. And now it's standard that the limit of n tends to infinity of x to the n is 0. So fn of x equals x to the n tends to 0, which is equal to f of x, and then tends to infinity. So no matter which x you take, if you fix that x and let n vary, you get a sequence tending to the right value. So combining the cases, for all x in the closed interval, we've got fn of x tends to f of x and then tends to infinity. It's a separate thing to look at for each x separately. You have a separate sequence to look at. But we've now established, by doing this case-by-case analysis, that it doesn't matter which x you check, the sequence converges to f of x, which is 1 at the right-hand end and 0 everywhere else. thus Fn tends to F pointwise on D, or pointwise on 0, 1. So why is it not uniform? Well, one reason is this standard fact that I'm letting you quote, that a uniform limit of continuous functions can't be discontinuous. So once you can quote that fact, then you can save yourself a bit of work and say, we happen to know that uniform limits of continuous functions have to be continuous, and you can quote that. That's, of course, easy, except that we haven't proved that uniform limits of continuous functions are continuous, and we won't have time to. If you want to see the proof of that, you can look in the books, but you are allowed to use that fact if you want to. However, I think that it would be worthwhile going back to the sketch of the sequence of functions. Once people have had a chance to write this down, we should go back to the sketch of the functions, and I'll just draw you what the function balls look like, centered on F. It's a bit difficult to, it's quite hard to do for this one, because the function ball is a bit odd. Now, you only have to find one bad epsilon, and I claim that epsilon equals a half would do, but I'd rather go for, in fact, any epsilon less than 1 would do, I think. Yes, any epsilon less than 1 would do, but it's a lot easier to see what's going on if you take a smaller epsilon, like epsilon equals a quarter. Because if you take epsilon equals a quarter, when we go back and draw what would be the curvy strip has a jump in it. The curvy strip, which has to go between the limit function minus epsilon and the limit function plus epsilon, goes along round the axis for a while. So let's go back, and I'll draw you this curvy strip. Let's go for a quarter. So I'll just go down here, a little bit further down. Hold on, let's make that black, so that I've got room to go a quarter. At the end, we're going to be jumping down to 3/4 and up to 5/4. And now I'm going to show you what the curvy strip centered on y equals f of x look like. Well, it goes along at height a quarter and minus a quarter. But then at the end point, it suddenly jumps up. That's why it's so hard to draw this one. And you get one little line segment up here going round that point, which is part of your function ball. So the function ball be a quarter of f is in grey. And as you can see, it goes along as a nice rectangle centered on the axis, but that right-hand end is not included, so I guess perhaps I should just dash it. Now this diagram is getting a bit messy, a bit harder to see, but as I hope you can see, it's most of this rectangle, but with the right-hand line segment suddenly shifted up by 1 unit. Now because of that, you can't actually get any continuous functions inside that function ball at all. Because any function that stayed inside that function ball would be stuck in the lower rectangle until it got to the right-hand end, when it would be supposed to suddenly jump up and take a value in the other little interval. But no continuous function could do that. In particular, none of these functions do that. As you can see, what these functions do is they go along near the axis for a while, and then they get very steep, and of course, somewhere near 1, but just below it, they'll take a value near 1 instead of being in the bottom rectangle. So what I would say about this, and I'll write this down in a minute once you've had a chance to draw anything you want to draw, is that this closed function ball, radius a quarter, centers on f, has no continuous functions in it at all. In particular, none of these functions are in it, the fn of x's, and so it certainly can't absorb that sequence of functions. So I'll just write that down now. So to show uniform convergence fails, we need just to find one bad value of epsilon. For example, epsilon equals a quarter is an easy choice. So see the sketch above for what the closed function ball be a quarter of f looks like. That function ball has no continuous functions in it. Because of the jump at 1. But in particular, none of the functions fn are in this ball. So that ball doesn't absorb the sequence of functions we're dealing with. We've done much more than failing to absorb it. It's not just the case that they aren't eventually stuck in there, it's even that none of them are in it, which is much more extreme. And as I say, for it to converge uniformly, it's supposed to be that every closed function ball absorbs the sequence. So as soon as you found one closed function ball that doesn't, you've finished. It doesn't converge uniformly. So Fn does not converge uniformly to F. Uniformly on 0, 1 to F. Which makes the next example a little bit strange because we use the same formula. We use the same formula, but this time we claim it does converge uniformly to the function 0. Why is that? Because we're working on a different interval. We stay away from the bad value x equals 1. We just stay between 0 and a half. And although we won't have time to finish this off today, let me give you some estimates that we'll be working with later. If 0 is less than or equal to x less than or equal to half, that implies that 0 is less than or equal to x to the n is less than or equal to 1 over 2 to the n. So actually, I mean, this is actually a very quick one, so I think we could finish it off. So let's let epsilon greater than naught. We have to show that the closed function ball centered on the zero function that's the same as f. That's supposed to absorb the sequence. Well, all you do is you choose n, a natural number, large enough that 2 to the minus n is less or equal to epsilon. Then, for all n greater or equal to n, and all x in the range 0 to half, we have modulus of fn of x minus 0, which is what we're estimating, equals modulus of x to the n is smaller or equal to 2 to the n, which is smaller or equal to 2 to the capital N, which is smaller or equal to epsilon. And that's exactly what you have to establish. At all points of the domain simultaneously and for all little n greater or equal to n, you're close enough to the function. So this shows that the closed function ball, b epsilon 0, absorbs fn by stage capital N. As required. And remember, uniform convergence implies pointwise convergence, so of course it converges pointwise as well. We'll stop there for today.
And that brings us on to the third and final session of Chapter 9, which, as far as I know, was not affected by any incidents.
Okay, last time then, we were looking at uniform convergence, and we talked about function balls, and then we looked at this example to start with, the functions x to the n, and we first defined them on the closed interval 0, 1, and we saw that they converged pointwise to this funny discontinuous function in orange, which went along the axis until it reached x equals 1, when it suddenly jumped up and had a discontinuity. So we had pointwise convergence of this sequence, but not uniform convergence. And then I quickly tried to show you a second example defined on the interval 0 to half. And as always happens if you try and do things in a hurry, there was a slip in what I wrote down, which I'll show you now. So started off okay. I did note that x to the n was between 0 and 1 over 2 to the n. And then I said let epsilon greater than 0, and I wanted to prove that this function ball, this thin strip, which is a thin rectangle centered on 0, should absorb these functions. Remember, we're working only on the interval 0 to half. And then I said, go far enough along that 2 to the minus n is less equal to epsilon, and that was fine. And once you've gone that far, your strip will absorb the functions from that point on. And then I wrote some rubbish, because I missed out 2 minus signs because I was doing it too fast. And I said, how close is fn of x to 0? It's at least modulus of it's exactly modulus of x to the n. And assuming that n is, well, we know that that's less equal to 2 to the minus n. That's 1 over 2 to the n, which is 2 to the minus n. And then because n is at least as big as capital N, that's less than equal to 2 to the minus capital N, which is indeed what we chose to be less than equal to epsilon. So I'd been all right if I hadn't missed out those two minus signs, but I did also say it without the minus signs, which is more embarrassing. But anyway, that's fixed now. So there are the two typos, and now we'll move on from there. So here's an interesting sequence of functions. This is a bit like a sequence of functions that we just dealt with in the examples class. So I'll just show you what these ones do. Like the ones in the examples class, they start from the origin, go up in a straight line to height 1, and then, but this time, they carry on at height 1 forever. And the gradient they go up with is 1 over n. So let me say explicitly that if 1 of x is x, if naught is less than or equal to x is less than or equal to 1, and 1 if x is greater than 1, if 2 of x is x over 2, if naught is smaller than x is smaller than 2, and it's 1 if x is bigger than 2, and so on. So you can just substitute in each value of n, and you'll get the definition of these functions. So now I can sketch them for you, and I've already described them. They go up to height 1 and then carry on at 1 forever. They all take values between 0 and 1. So I can sketch them on the positive real axis like this. So if 1 of x goes up like y equals x until it hits height 1, let's get my height 1 going across properly. And here's y equals f1 of x. Y equals f2 of x does the same thing, except that it doesn't get up to height 1 until you get over to 2. F3 of x does the same thing at 3. I think I'll go under this time. You see, it's actually very difficult to do this properly because you've got to indicate all these different functions which are still going along the same line. And finally, I'll stick it at F4 of x, which gets to here, if I can, and off it goes. And they all go off forever along that straight line. But I can't bother to put all the dots in. Anyway, I've run out of room at the right. So they stay at height 1 and off they go. Well, these functions are very like some other functions I asked you to look at earlier. And you can check quite readily that they converge to 0 pointwise. Show that Fn tends to 0 pointwise. I'll give you a hint for that, though. You can use the sandwich theorem. if you've already done the other one. Hint. If you want to avoid doing case-by-case analysis is also perfectly fine, but note that naught is smaller or equal to fn of x is always less or equal to x over n, which tends to naught as n tends to infinity. So you can use the sandwich theorem. I'll let you fill in the details of that. But it doesn't converge to 0 uniformly, because if you take a little thin strip centered on 0, if you take a thin horizontal strip centered on 0, you get something looking like this. And let me choose a height. Let's say that's a fifth. It doesn't. You should choose a specific value for your bad epsilon. So that's minus a fifth, and that's a fifth. It doesn't converge uniformly because none of these functions are stuck in that grey strip. The functions always get out of that grey strip because they always manage to get up to height 1 somewhere. So none of them stay between minus a fifth and a fifth. So none of the functions fn are in that grey strip. So this function ball, those are the functions that get stuck inside the grey strip. And we've seen that they all escape because they all manage to get up to height 1 somewhere. So that gets them well outside. Did I say sixth? I think I was going for a fifth above. It doesn't really matter. You have to choose what epsilon you want and stick with it. None of the functions are in there. So that ball does not absorb the sequence in particular. Again, we always got these extreme examples where the ball not only doesn't absorb the sequence, but none of them are in. That's what we've been doing so far. And so the sequence does not converge uniformly to 0. Any questions about this example or in general about uniform convergence? Yes?
Why don't you take a big epsilon instead of a fifth, take it greater than 1?
Okay, so if you took an epsilon bigger than 1, it would be absorbed. But for convergence, it has to be every ball absorbs it. So for uniform convergence, it should be all epsilon, it works. So to show it doesn't converge uniformly, you just have to find one bad epsilon. And so that's a good point. There are some epsilons that work, but for it to be uniform convergence, all of them must work, and it's the small ones that count. Because if a small one works, the bigger ones do as well. So you only really need to check really, really small epsilons. And if they work, if all of the really small ones work, then you're home. But if you find a small one that doesn't work, then you've proved it isn't uniform convergence. So yet again, you only need one bad epsilon to fail uniform convergence. Any more questions about these examples or uniform convergence, pointwise convergence before we finish off this chapter? Okay? It's pretty tricky stuff, this. It's probably harder than anything else we've done in the module. So if you can get used to all these examples of sequences of functions, you're doing really well. If you look at question sheet 5, you'll see some discussion of something called the uniform norm, which measures how far apart two functions are uniformly. And that gives you a notion of distance between two functions. And if you use that notion of distance between functions, you can get the notion of convergence using that distance. And everything becomes a slightly more, it's a slightly more standard way of looking at things to use a uniform norm. But you don't usually define uniform norm unless you're dealing with bounded functions. So my approach with the function balls is very slightly more general because you don't have to be dealing with bounded functions in the first place. But they're very closely related, as you'll see if you look at question sheet 5. So uniform convergence is much stronger than pointwise convergence. We see lots of examples of pointwise convergence where you didn't have uniform convergence. We've seen how to establish pointwise convergence. In at least one example, we did it in full. We've seen how to establish uniform convergence. It's a bit harder, but we did see one example of that. And we see lots of ways to show that things don't converge uniformly by finding one bad epsilon. Now, why is uniform convergence so much better than pointwise convergence? Because pointwise limits of continuous functions may be discontinuous. We saw examples of that. That first example we looked at, we had a sequence of continuous functions and they converged to a discontinuous function. The functions x to the n defined on the closed interval 0, 1. They're really nice and continuous, but the limit function had this funny jump when you got to 1. But uniform limits of continuous functions are always continuous. But we don't have time to prove it. I usually prove this in my 4th year module on functional analysis. Sometimes it gets proved in the 3rd year module on metric and topological spaces. But basically it says a uniform limit of continuous functions is continuous. So if you do have continuous functions and they converge to something uniformly, the limit must be continuous as well. You're allowed to state that result now. You're allowed to state it because I've told you it, even though we haven't had time to prove it. And the nice thing about me letting you quote that is that you could go back to that first example where some continuous functions tended pointwise to something that was discontinuous, and you don't actually have to bother with drawing the grey rectangle anymore because you can say, well, the limit is discontinuous and the functions are continuous. They can't possibly converge uniformly to a discontinuous limit. So you already know that they're not converging uniformly for that reason. But of course, we haven't proved that theorem. But you're allowed to quote it as a standard theorem. And if you want to see a proof, you can find it in the book of Wade. So uniform limits are very good. But other things can happen as well. Pointwise limits can be very bad in other ways. A sequence of bounded functions can converge to an unbounded function pointwise, and a sequence of unbounded functions can converge to a bounded function pointwise. I'll leave you to think of some examples. Doesn't happen for uniform limits. Let me not bother with all that stuff. I've already said that basically. So let's move on to some final facts about uniform convergence. So proposition 9.1.7, the idea of this is to show that a sequence of unbounded functions cannot converge uniformly to a bounded function. But the first part of this is to note that if you've got a bounded function and you look at some function ball and you've got another function in that function ball centered on a bounded function, then they're bounded as well. And although I'm not going to prove that, I will give you a little sketch of it. So I'll draw a little sketch of that thing in a moment. Once you know that, you get the second one for free, because if everything in the function ball is bounded, then none of the unbounded ones can get in there. So if all functions in the epsilon function ball are bounded functions, then none of these approximating unbounded functions could be in that function ball, or else they'd be bounded functions. So if you can prove one, you get two for free. So all you need to know is that if you're in some function ball centered on a bounded function, you're still bounded. And then, as I say, what you get is it's impossible for things of unbounded real-valued functions to converge uniformly on your domain to a bounded one. And it's the same the other way around. It's impossible for a sequence of bounded ones to converge uniformly to an unbounded one. Pointwise convergence is another matter. You can find examples for yourself of sequences of functions that do all sorts of strange things pointwise. So the key to all this then, is that you suppose you've got a bounded function. If f from D to R is bounded, then say minus m is less than or equal to f of x is less than or equal to m for all x in D. And then if G is in that little epsilon ball centered on F, then the smallest G can be is minus m minus epsilon, and the biggest G can be is plus m plus epsilon. So that's G of x for all x in D. And of course you could draw a little sketch of that. So if this is y equals f of x, I don't like that one. I'm going to draw a slightly different one, sorry. Then I'll draw the function ball. Come back. Too far over again, sorry. And then if G is somewhere between those two, which is what you need to be in the function ball, well, you can see G is stuck between f of x minus epsilon and f of x plus epsilon. F is bounded, so G is almost as bounded as f is. It might get a tiny bit bigger, it might get a tiny bit smaller, but if f is bounded, so is G. And you could use the same reasoning to show that if f is unbounded, so is G. And that's how it works. Any questions about that before we move on to the next chapter? If not, I'll give you a 2-minute break, a chance to pick up any handouts if you haven't got them.